I told you I was going to talk about plastic hardening. I'm not really going to talk about plastic hardening. I'm just going to show it to you in the documentation and give you the 5-second version. It's a fairly advanced topic. It's sort of beyond the scope of the introductory training. If you go to the docs and you go to the documentation, you don't have to follow along. I'm just going to show you. One of the constitutive models you have the plastic hardening model. And what is interesting about this model is this curve here. So, should I make this bigger? So the reason that this model is fun is that here you've got your shear stress and your strain one. And so for like Moore Coulomb and all these other models, you basically start with a straight line, right? So that the stiffness is related to the Young's modulus and Poisson's ratio, and it just increases linearly. What makes this model interesting is that stiffness is nonlinear. Okay, so as this thing is loading up, it actually becomes less stiff, and it follows this hyperbolic line. And so you have somewhere in here is an equation that tells you what the modulus, the shear modulus. I can't put my finger on it, but somewhere in here is the shear modulus is nonlinear, right? It depends on where you are on this curve. So the thing gets less stiff as you go along. But if you unload, it becomes stiff again. So somewhere in here, there should be unloading and loading. Let's go to the examples. So if you go down here, model tests and examples, there's a bunch of tests for the plastic hardening model. There you go. Comparison between Moore Coulomb model and plastic hardening model. So this is just a simple little one-zone model, I think, but it sort of compares the behavior of the two different things, right? So this is just, now we're just talking about axial stress versus axial strain. You load this thing up, you can see the plastic hardening model curves and becomes less stiff compared to the Moore Coulomb model. But what's interesting is if you do these little unload reload excursions, it's still stiff, right? So the whole point of this thing is that you have some soil that's loaded up, you excavate, and you want it to be stiff during the unloading, right? You don't want to get this like super excessive rebound that you see when you're using sort of Moore Coulomb model. So it's stiff during the unloading and reloading, but it's less stiff if it's sort of normally consolidated, right? That's pretty much all I'm going to say about that. I'm not an expert in this field. If anybody's doing UDM tomorrow with Joe, he can talk about this all day long. Point is that this model is quite popular now in the soils world, probably more so than Cam Clay, I think. Our own consultants that are doing civil engineering use this all the time. So again, it's worth becoming familiar with this and going through some of these simple examples if you're interested. We're not going to do that right now because beyond the scope of this course. Okay. The second topic that we didn't get to the other day was factor of safety contours. So you can we can follow along here for this. This will take like 10 minutes, but it's kind of interesting. If you start FLAC2D, and so I've given you a project. If you go to Where did I put it? A1, FOS contours. You can open that project, FOS contours. We're not going to type anything here. It's all there for you already. If you double click on the initial save state, and just click on the FOS plot, you can see what this model looks like. So it's a slope, but it's a bumpy slope. It's got a few different sections to it, which is different from the super simple slope we did the other day on Monday. And so the point of this is that you could potentially have multiple failure surfaces, right? There might be, when you do a factor of safety analysis, it's going to give you the absolute worst case failure surface, which is, probably down here somewhere. But you might be interested in a more global failure surface, or you might be interested in what's happening up here, or something like that, right? And just doing this factor of safety analysis doesn't necessarily give you that resolution of possible failure surfaces. But what it does do is a funny little trick. So every time it does this factor of safety calculation, so it weakens the cohesion and the friction, does the factor of safety calculation, and it saves the velocities of all the grid points at the end of that calculation. So for every one of those tests of factor of safety, it saves the velocities. And what it can do is it can then use those velocities to sort of plot a map of failure surfaces, so to speak. So if we click on final, so double click on final here. And then click the plot for FOS contours. Does yours look something like this? I was messing around with it at home, so maybe yours is slightly different. But so what you can see here is this is essentially a contour map of factor of safety. So you've got this dark blue region here. This is the sort of global worst case factor of safety, 1.6. And then you've got this sort of, or maybe 1.65 maybe. Then you've got this sort of different color blue. So you can see how there's kind of like two slip surfaces going on here, right? And then you've got this global surface here that's maybe like 1.8. And the way that it does this is that it takes those velocities that it saves and uses them to dictate what the factor of safety is. So if you click on the plot item list here, zone factor of safety, you can see one of the attributes is velocity limit. So this is a little bit arbitrary, right? It just comes up with a velocity threshold and says, okay, if the velocity is greater than 4e minus 6, I'm going to say that that part of the slope is failing, right? So it does, let's say it does the factor of safety analysis and it does, 1.8. These sections of the slope have a velocity faster than 4e minus 6 in that case, right? It's kind of arbitrary, so you can actually change this number, and you get slightly different answers. And I don't really have super good advice as to what number you should use there, except I always just use the default. It just, again, it's not super duper accurate, but it does give you some idea of multiple different possible failure surfaces, and roughly what their factor of safety would be, if that makes sense. So I don't know. It's just kind of a handy fun thing you can use to look at these things in a little bit more detail.